Okay, welcome to lecture number 50. In this lecture, we will study some properties of altitude configuration, which is also known as orthic configuration. Now, if you draw triangle ABC and if we put three altitudes, we have proved it couple of ways that these three altitudes pass through a common point, and that common point is called orthocenter, denoted by H. Now, if you observe that these angles are 90 degree and altitude is the line that we draw from the vertex of triangle to the opposite side. So this is the altitude drawn from A to BC, B to AC, and C to AB. Now, if we consider triangle ABC, that means points ABC, then H is orthocenter. But if we consider triangle HBC, what is the orthocenter of triangle HBC? What we should do is draw line from H perpendicular to BC. That means this is the same line. Then draw line perpendicular to CH passing through B, which is this line, and draw line through C passing perpendicular to AB, which is this line. So again, these are the three same lines, they intersect at A, and orthocenter of triangle HBC happens to be capital A. Similarly, HAC will be capital B and HAB will be capital C. So if you take any 4 points HABC and create a triangle using 3 points amongst those 4, and the 4th point happens to be the orthocenter, then we call this particular configuration as orthic group of points. These four points are said to be forming orthic group. You take any 3, 4th is the orthocenter. Okay, that is the first part of our lecture. Then what we are supposed to prove is many properties of this altitude configuration. So let us use the same diagram and keep discovering different properties. Now, this lecture we allow students to find out many more properties in this particular configuration themselves in class, but in this format basically I would just ask the question and immediately tell you the answer. So if I join these lines, so I have got triangle BEF also now, and triangle ABC, DE and F are feet of perpendicular. So how many cyclic quadrilaterals are there in this figure? That is my first question. Cyclic quadrilaterals are there in this figure. There are 3 angles which are 90, which are altitudes with the side of the triangle, and therefore there are total 6 cyclic quadrilaterals. Quadrilateral AFHE, quadrilateral BDHF, quadrilateral CEHD. These are 3 of one type, and BFEC, then CDFE and AEDB. These are the 3 of other type. The first ones are the ones whose opposite angles add up to 180, and the second ones are the ones whose inscribed angles are 90. Okay, so if inscribed angles are 90, the midpoint happens to be the A dash. Midpoint happens to be the center of that circle. A dash, B dash, C dash are centers of the corresponding circles if we happen to draw circle around that cyclic quadrilateral. Okay, so this is the first finding, that there are about 6 cyclic quadrilaterals in this figure. Now, the moment we say that cyclic quadrilateral is there, there are many angles which are equal. Say for example, we wish to know what is this angle equal to, which is FBE. Angle FBE is going to be equal to, if we consider cyclic quadrilateral BFEC, then EF makes X angle at B, EF will make X angle at C. So this angle is also going to be X. Now if we consider HFBD as a cyclic quadrilateral, then HF inscribes X angle at B, therefore HF will inscribe X angle at D also. So angle at D is also FDH is also X, and similarly if you consider HE inscribes X angle, HE will inscribe X angle at D. So these four angles are always congruent in orthic configuration. So if it is true for this, then Y and Y, we can easily prove that these four angles are also equal, then these four angles are also equal, they are equal to Z. So there are many angles which are equal. Now if we consider quadrilateral BFEC, then this angle happens to be exterior angle of that cyclic quadrilateral, which is supposed to be equal to remote opposite interior angle, and therefore this angle happens to be B, this angle happens to be C, and this is anyway angle A, right? So this angle, if we consider AFDC, then this angle happens to be C. This angle is going to be B, and this is A. This is also A, this is C, and this is B. So capital B's are available, capital A's are available, capital C's are available at different places, and we can actually write all the angles in terms of X, Y, Z's. Okay. Now this angle is, so this angle is C, AFE is C, and we said AFHE is cyclic. Therefore, you will observe that this angle here is also C. This angle here is B. This angle here will be A. This is vertex opposite, therefore this is C. This is B. This is A. So practically here we have found almost all angles related to this particular configuration, and therefore there are many similar triangles. So second thing that we would like to write is triangle ABC is similar to triangle AEF, because it is ABC, is similar to triangle DBF, is similar to triangle DEC. Right? So these are similar triangles in this figure that we have found out. We have found out different angles. Now another observation here is this angle is X, this angle is X, this angle is Y, this angle is Y, this angle is Y, this angle is Z. Therefore another observation is H is in center of triangle DEF. H is in center of triangle DEF. Another thing, using the same angle chasing, you can find out that say A is X center of triangle DEF. Similarly, B, C are X centers of these triangles. Then, using similarity, some similar triangles in this configuration, we can eventually prove few more results. The results include basically AF, AB is equal to AH, AD is equal to AE, AC. This is by using PAPB is equal to PCPD we can do it, because there exists a circle passing through these 4 points and A is the point which is outside. There exists a circle passing through these 4 points and again A is the point outside, therefore it is PAPB is equal to PCPD written for this configuration. Then there could be DBDC is equal to df de is equal to dh dA. This is also true. Now these ratios, these things you can very easily prove. Maybe I will show you one. Suppose I want to prove this, then I have to write it df upon dh is equal to dA upon dE. So if these two things are equal, these two ratios are equal, then this is going to be true. So in this case I will say, let me check whether triangle FDH is similar to triangle ADE. If FDH is similar to triangle ADE, then my job is over. FDH is the triangle having XZ and A plus C, and ADE XZ, these are the two angles XZ XZ. So these two triangles are similar, and therefore I get this result. So it is easy. Once we have completed the angle chasing in this configuration, almost all the questions that we have asked here can be easily found out by angle chasing. Okay, the last one, 11th one in this list is circumcircle of triangle ABC, HBC, HAC and HAB. They are equal, congruent. Now I think in last lecture we have seen that if the base is same and if the angles inscribed, let me revise, if two congruent segments, then this is X and this angle is X, and suppose another angle is also X, these two segments are congruent, and when you put circumradius of this triangle and this triangle will be equal, because they will be inscribed angles once they put one above the other. Another situation that we have studied is if these two segments are congruent, if one angle is X and another angle is a supplement of that, X plus Y is equal to 180, then also circumradii of both these triangles will be equal. And now therefore we should be able to find out circumradius of triangle ABC and triangle HBC. How should they be? Now you will observe that this total angle is B plus C and this angle is small a. So if I flip this triangle BHC the other side, then C plus B is going to be supplementary with A, and therefore it will be a cyclic quadrilateral. So here what is happening is angle A above BC, I have angle A, and above BC I have H, but A plus H, if I add these two angles, they equal 180. Therefore by this situation the circumradii of HBC and ABC will be equal, and similarly I can prove that circumradii of HCA and HAB also will be equal to triangle ABC. Okay, so what I will suggest is one by one you should try and prove these 11 results, 12 results independently, 11 results independently, and master this configuration. You need to keep looking at this configuration for hours together, and then you will master it. And there are many properties which are hidden into this, you will come to know. Once you are done with that, solve these homework problems, 10 homework problems, and they are interesting numericals, so you should be able to solve it. Else take our help and complete this lecture. See you in lecture number 51. Thank you.